part I didn't say on camera. Awesome. Okay. So if anybody's watching this on YouTube later, here is the new retake policy for A&P 1 for this semester. Oh, there's one concept I wanted to go over before we move forward with the stuff in the rest of this PowerPoint. So I've gotten multiple questions about spatial summation. And really, I think you guys are overthinking this, but I want to just clarify it. The concept of spatial versus temporal summation should actually be really easy. So the way you could think about it, maybe, so let's pretend this room is our neuron. So say I was doing a weird thing and I start, say I'm early to class, I'm gonna start class as soon as there are 10 people in this room, right? That's like our threshold. Okay. So a way that could happen for temporal summation is say like 5 of you come in chatting as a group, we wait a little bit, and then 5 more of you come in later from a different class. Then we're at 10 and I start. Okay, so that's temporal summation. Spatial summation is if I'm in here, I have the doors closed, and then I like open 2 doors at opposite ends of the room. So pretend this partition is open and the other door over there is open as well. And then you have 5 people coming through this door, 5 people coming through that door, and so I start the class. Does that make sense? Yeah.
It says help. This is how I thought of it. In spatial summation, if 2 people punch you in the face, it's going to have a bigger impact than if 1 person punches you in the face.
Yeah. Yeah, true. Yeah, so it's really just 2 spots at once. That's it for spatial summation. And those numbers that I was throwing up last time, like that it goes up 10, it goes up 8 or whatever, you don't have to do anything with those numbers. That's just like kind of how I think about it conceptually. All you need to know in terms of numbers is that our resting membrane potential is -70. Our threshold that we're trying to get to is -55. If we get up to or above -55, we'll do the action potential, and we'll see on some numbers there. And if we don't, it just stays a little graded potential and it fades away. So I was just kind of trying to show with those numbers like how they would add or like what that decrease as we move away from a graded potential means, but you don't need to do any of that. Okay. Other questions about the stuff we went over on Wednesday, any like course business? Okay. Cool. So when we left off, we were talking about these voltage gated sodium channels. I'll take another refresher look at them just because I find that these can kind of be a little confusing as well. So basically, the reason we care about these voltage gated sodium channels is they're going to shoot off our action potentials. These are what is responding to that, reaching that threshold as we add together graded potential. So the reason we're trying to get to -55 millivolts to fire off an action potential is that at -55 millivolts, there's a change in these voltage gated sodium channels. So the change specifically, so when we're starting out with our voltage gated sodium channel, we have 2 gates. One of them is open. So if that was the only gate, we'd have sodium coming in because we remember that that's the direction sodium wants to go because of our electrochemical driving force. So we have a second gate in the center called our activation gate. That's closed. So at -55, what happens is that membrane potential causes a reaction such that our activation gate opens. So nothing's happening to the inactivation gate here, it stays open. But now that our activation gate is open as well, we have a clear shot through. Eventually, to close this off, because this is going to be raising our membrane potential up and up and up as we're getting towards that positive 60 equilibrium potential for sodium. We do close off these channels, and that's what the inactivation gate is for. So the deactivation happens around the time the membrane potential gets to positive 30. A little bit after that, but yeah, so they'll eventually go back to rest. Yeah. So yeah, when we see it, when we look at the action potential, we're going to see the spike up to positive 30. Then we're going to see our repolarization down a little bit like this. And there's actually something called a refractory period between action potentials. So there's only like so frequently they can fire. They need to have like a little period of rest between. So that's kind of when this is happening, that going back to this original state. So there's an element kind of like of time delay on that, basically. So activation gate, voltage dependent, immediately responds to that negative 55 threshold being crossed. That's opening, allowing sodium to rush in. So technically, this is an example of positive feedback because we have a bunch of these voltage gated sodium channels around, right? There's not just one. And now that we're talking about the neuron, right, we've expanded our idea of the cell and the membrane potential as like not the whole cell changing in charge at once. We've added on this idea that different parts of the cell can have changes in charge versus like a little bit of the membrane somewhere else. So what happens as we start to have sodium rushing in through one voltage gated sodium channel is that brings in a bunch of sodium ions that start to spread out to neighboring areas of the membrane, which means that they hit thresholds, that their sodium channels open. And that's how we get this spread around the whole cell. Is that as some sodium channels open, it opens more and more of them because more and more sections of the cell are reaching this threshold. Exactly, it's definitely a domino effect. Actually, you can almost think of the action potential when we see it running down the axon as literally a row of dominoes. So the inactivation gate similarly responsive to the voltage. So technically it's also responding to that threshold, but has like a time delay on it. So it still responds to the fact that we have a change in membrane potential, but it's slower, which is why it doesn't swing closed until we get to that like positive 30. You guys have a question?
Like, are you serious? Like, continuous loop?
So this is almost kind of like a reflex when we first cross that threshold. So we are going to see more sodium channels opening, but it's really going to be, this is happening here in these sodium channels, and then it's going to happen in the next set, and then it's going to happen in the next set, and then it's going to happen in the next set. So they do reset, but they don't just like keep going until we have our next action potential fire.
And after all this goes into the cell, that's when you go back to like the stuff we previously talked about, how we start to push out again, right?
We are going to start talking about what happens next because we are also going to have an effect of voltage gated potassium channels. Yeah, so we're not going to get all the way up to that sodium equilibrium point. So we're actually going to still have this force for sodium to move in. It's just that we're going to block off these channels, so it can't. And our voltage gated potassium channels are going to open up, and they're going to allow potassium to leave, which is going to drop our membrane potential back down. So when we talk about the phases of the action potential, which we will label on our little graph, we would say that when the activation gate opens, this is kind of going to start our depolarization phase. So if we're talking about the inactivation gate, we're going to say that it's opening during depolarization, but it also closes during depolarization. Segueing us perfectly into the next thing, we have our voltage gated potassium channel. So far, right, we had our little graded potentials, they were whatever, maybe they summed together, and they got us to -55. I'll draw a little dotted line for our -70 millivolts. And let's say here, we got to -55. Maybe I should make this peak a bit bigger to be the scale. So here is where we had our sodium rushing in. Okay. So that was our depolarization portion of our action potential. So we're about like here. So the peak of this is going to be around +30. And the reason we're going back down now is twofold. So the first part is that inactivation gate on the voltage gated sodium channel has closed. So we can't really get more sodium in, right? So it's not rushing into the cell anymore because that channel's not closed. But that would just kind of leave us hanging out here at +30 if it was the only thing that's happening. So the reason that our action potential then takes a dive and repolarizes, just right at the top here, and you guys have plenty of images of this action potential in not my little chicken scratch drawings. But you'll probably see me draw it again and again anyway. But the reason the cell is going to repolarize and go back down is because sodium isn't coming into the cell anymore, but we're opening these potassium channels at the same time. So we should remember, if we don't study and then remember, that potassium wants to leave cells because it's trying to get the cell to -94 millivolts. That's its equilibrium potential. So when these voltage gated potassium channels open, this means we have positive channels leaving, positive charges leaving the cell. Actually, we talked about initially when we were setting up the resting memory potential, there wasn't very much force for potassium to leave the cell. But that's because we were down at -70, we were really close to equilibrium potential. So there's much more of a force than there was before. Once we're up at that peak of the action potential, once we're at +30, we've moved a fair bit away from our equilibrium potential for potassium. So that's why we really do rush out of the cell at this point. So it wouldn't really happen fast if we were down at -70, but because we're at +30, there's a greater magnitude to this force. So that's why we're repolarizing, because our cell is losing positive charges in the form of potassium. We don't need to think very much about the structure of a voltage gated potassium channel because it's not very complex. It really just has a one gate. So it doesn't have the same 1-2 thing going on that the sodium channel does. It's just either open or closed. So potassium voltage gated channels have one gate. It depends on the voltage, they are voltage gated, but it also has this timing component. There's a little delay here as well. So we might consider this our negative feedback because we've gone up and up and up, right? We were rushing way up, almost asymptotically with our sodium channels opening. So that was positive feedback snowballing up, but now we're pulling back down. So this is kind of our negative feedback on this change in charge. short break for you to answer some questions for me. Okay. Great. Yeah, the sodium channels are the ones with 2. Potassium just has 1. Okay. A little trickier, but hopefully not that tricky. Activation gate for the sodium channel is open or closed when we start out at the resting membrane. When we start out at rest, the activation state is closed. You're just going to have to stare at these words for a while. The activation, inactivation, for some reason, it's kind of easy to scramble in your mind potentially. So our sodium channels are closed. So our sodium channels kind of are inactive.
I feel like it's easier to think about it as the inactivation gate is inside the cell versus the activation outside.
I like that.
And you know that the inside one is going to stay closed, like if you can memorize that.
I like that. I like that. Inactivation gate, the one inside the cell for anyone who didn't hear or who's watching it later. I assume that microphone is over here. Okay. Which means what's going on with our inactivation gate at rest when we start. Great. The inactivation gate is the one that's open. That one hanging open on the inside of the cell is open. So they're in opposite states when we're at rest. One's open, one's closed. When we're firing off our action potential, when we're doing that rapid depolarization, both of them have to be open. Otherwise, sodium wouldn't get through. And then we're cycling back. Yeah.
Okay, I guess I don't understand when you say potassium is 1 and sodium is 2. What does that mean?
Oh, just that the potassium channel, it doesn't have like these 2 doors. It doesn't have an inactivation gate and an activation gate. It just has 1 door. So like if I'll scroll back and we'll look at them. So this is the potassium. So really we're just thinking about it as having 1. I know it kind of looks in the middle like it has 2, but it doesn't, it just has 1 gate. Versus the sodium one has 2 that we're paying attention to. So they're like 2 things that have to swing open. So think about it like, you know how sometimes like the door to a porch has like 2 glass doors that you have to open to get through? That's our sodium. The potassium gate is just like a normal door. You just open 1 door. That's it. So that's why we have to be a little careful when we're thinking about the states of the sodium one specifically, because it has 2, so the 2 things can be in different positions. But for potassium, we're just thinking open or closed.
Potassium open when the membrane potential got plus 30.
Mm-hmm.
Does it close again?
See it right here. So it's starting to close around here, right? So this is basically them closing. So almost we see it happening as we're getting back towards that threshold. Do we want to think of it more as like a time delay rather than a specific number that they close at? So they start opening at positive 30 And then as we're entering our next phase and we start to see this dip, that's when they're closing. So speaking of, what we're looking at here is a little messy, but this is kind of telling us all-ish. I won't say it tells us all we need to know about the states of the channels, but it is telling us about how the cell can respond to our sodium and our potassium ions. So red line is our action potential, which means it's our actual membrane potential of our cell. So that's what we're tracking if we're just trying to think about what's happening to the membrane potential, to the charge. And this purple line is our permeability for sodium. So that means how well sodium can get through our membrane. So it's kind of like how many open, fully open, let's say, fully open sodium channels there are. It's not exactly a number, but that's why we have it labeled on the other axis. Finally, that little blue line, permeability of the potassium. So we have how many plus channels are open. So a little bit difficult to see the obvious relationship here until you stare at this graph a bunch. But the sodium part is relatively easy, right? So our voltage goes up as our sodium channels open up. So that's responsible for that rushing in. And then we can see that as our voltage goes down, the permeability of sodium is going down. All right, so we can see that there is a down here for sodium. But closing sodium channels itself doesn't drop the membrane potential down. It just stops it from going up. So the actual cause of this drop in the red line is the fact that we're starting to open our potassium channels. So like basically we can think about the potassium as like we have to subtract this from our membrane potential. So that's why we have this down. So another way we can think about this when we're thinking about the action potential, right, for the depolarization, all you have to think about is our sodium, right? Basically, it's causing the sodium to come in, which means it's causing that rise. But for our repolarization, it's going to be dependent on the state of sodium and potassium channels. Does that sort of make sense so far? We have different versions of this picture over and over again over the next several slides. So hopefully at least one of these pictures will make sense if that one didn't. Okay. So the action potential is a change in the membrane potential. So we would say that the membrane is excitable because it's able to be excited, meaning it's able to have a depolarization, meaning we're able to have this change in charge. So a membrane that can fire off an action potential is an excitable membrane. The only reason we're being specific there really is we won't think about things like this if you're thinking about like an epithelial cell in your arm or something. We think about action potential really when we're thinking about neurons, when we're thinking about nerves, and also we'll see kind of like action potential to muscles as well. So it depends on the tissue whether we're going to expect to see these changes in voltage. They're not that important in other types of tissue, just these kind of communicative ones that are moving. So the action potential, formally, the formal definition here is that we have a rapid, large depolarization that's used for communication, and really it's going down our cell in like a wave. So it's a depolarization. An action potential is a depolarization. Super important to link those two words in your mind. If we're talking about an action potential in a neuron, is what we're talking about for right now. We've got muscles way in the future. The action potential is going to travel along an axon. Good, A and A go together. So it's going from the cell body. Okay, so we had like neurons in yellow, right? So we had our dendrites. We had our cell body. We have this pinching off, which is our axon hillock, into the axon, and then we're going to our axon terminals. So the place we're seeing this wave of depolarization, we're going to see it down the axon. So it's like going to happen here first, and then that's going to trigger it happening here, then here, and so on until it gets to the end. So if you were trying to put dominoes on your neuron, you'd line them up here down our axon. So they're going to go to the axon terminal or to another neuron. So yeah, basically. We'll talk about synapses after we go through everything that's happening in the axon. Okay. So here is another picture, another way we can think about this. Right. So our threshold. They put negative 50 on the graph, but we would know then that negative 55 is like here. So when we get to that threshold, sodium is rushing in, causing this peak up to positive 30. Okay, so they've colored here our blue. Here is that depolarization. Our green, they've made the repolarization. And then the yellow, they've colored our resting membrane. So that first part, that rush up is a positive feedback loop because our open sodium channels are triggering more sodium channels to open. Causes us to go way up. So we're going above our resting membrane potential for sure, above negative 70, but we're going above negative 55 as well, right? Because that was our threshold, and we're going above 0 all the way to positive 30, but not quite to positive 60, which is where sodium is trying to get to. That's why it's in such a rush. Okay. When we get to 30, those sodium channels are closing. So we don't have sodium making the cell more positive anymore. And we have our potassium channels opening, and potassium wants to escape. So they rush out. As we remove these positive charges, the cell becomes more negative. So this is pulling us back down to the negative. Here we can see a little table. If you are a table-minded person, of the states of all of our voltage gated channels and the flow of sodium and potassium in each of the phases of our action potential. So we talked about rest at -70. So this is normal when our neuron is just hanging out, not firing. Then we talked about depolarization. So that would be like our graded potentials adding up to -55 and that shooting up. They're both going in the same direction, so we can lump them together and call them depolarization as one thing. Repolarization as we come back down. And actually a feature of an action potential, you'll often see it drawn. It actually wasn't on that previous slide with the yellow and the blue, so I didn't label it. But actually it kind of overshoots often. So potassium kind of escapes a little bit too much. So there's an after hyperpolarization where that potassium gets a little even closer to its equilibrium potential than normal. So this is all due to whether our sodium channels are open, therefore allowing sodium to flow through, and whether our potassium channels are open, causing potassium to flow out. So sodium makes itself positive, potassium makes itself negative. And again, so still the action potential. We're still talking about this rapid, large depolarization. Good for communicating long distances because it's a bunch of falling dominoes instead of just a charge that relies on ions spreading out, therefore decreasing, which is kind of what our graded potentials did. Like they faded as we got farther, they decayed, they were decremental. So because the action potential is like dominoes, right? And there's one, and then there's another, and then there's another, it can go really far. Like you have nerves, right, that run from your brain down your spinal cord all the way to your foot, right? So they can go really, really far.
So that's the point of this, is like the communication between neurons. This happens all the time in our body. Like every time you feel pain, it happens that quickly.
Basically, yeah. So you're going to be measuring how long it takes in phys lab for. We'll see that there are some chains of nerves in our body, but it's not like there are hundreds of nerves in a row. It's like 2 or something when you're out in the body. So you'll be looking at how long it takes an action potential to get like from your spine to your calf. You'll be measuring it using that ILEC system. Does that answer your question? Yeah, so this is happening in neurons in your brain, but it's also how nerves out in your body.
But so open and close that yes, yeah, I'm just wondering like the application of this concept, like the sodium going in and the potassium going out, that's what regulates like all the communication in the body.
Yeah, basically. Yeah, which is why we really care about sodium and potassium concentrations in the body, right? Because you can imagine if the levels of the sodium in that extracellular fluid were something different, then that changes the chemical gradient, which means it changes the electrochemical driving force, which means we're screwed, right? Like it really messes up the action potential. So that's part of why, like, the kidneys kind of regulate the ion levels in your blood and therefore in the rest of your body. So that's why one of the things they look out for when they're thinking about kidney problems is like, how salty is your blood getting, right? Like those are actual diagnosable problems if you have an imbalance with sodium or potassium. So yeah, wild, right? Scary. But it's okay, your kidneys do a good job, so you don't really have to worry that much about eating salt unless your doctor tells you so. So when your kidneys are functioning normal, you should be good. So yeah, they're traveling a really long way, and it's all due to these sodium and potassium gradients. More pictures of this. So in this image, they've showed us the stimulus getting us up to -55. as well as that first part of the action potential. All of this being depolarization. And here we have the potassium rushing out during the repolarization. They haven't mentioned that our sodium channels have closed here, but they have. So we can see here, basically, in a much more confusing form, that when we have the stimulus, that stimulus is causing sodium channels to open, causing sodium to come in, which means our charge is going up. So we have this positive feedback loop here in green, causing more and more sodium channels to open. And the other thing we have happening on the other side here is that our potassium channels are slower to respond, but ultimately they're still responding to that same stimulus. So when they open, our potassium goes out, causing the cell to become first less positive and then actively negative, causing less depolarization. And this is not really a loop because they're not really responding to the state of the cell at that moment. They're responding to the first voltage change. But it is negative. Okay. So here we see that picture with the permeability again. So we could compare using those greater less than symbols, whether the permeability for potassium or sodium is greater. So covered on Monday, I believe, that at rest, at our resting membrane potential at -70, we're at -70 because the membrane is more permeable to potassium at baseline. Right? That's why we're down that far. That's why we're that close to the equilibrium potential for potassium. Really far from the sodium, but the membrane isn't very permeable to it, so not much sodium can get in. This changes when we hit the threshold. So we depolarize the threshold. Depolarizing, remember, really that's just a word meaning that the charge is going up inside the cell, getting positive, more positive than -70. The depolarization as our gradient potentials add together, and then we hit our threshold of -55. Hitting that threshold means we have all our sodium channels opening in that area. They do then close after, and then they'll be able to open again if we have another stimulus return the cell to that -55 after we drop back down. So it could happen again. That's what it means by saying this is regenerative. Like it's not like your neurons can fire off one action potential ever. They close slowly, so we don't start to see those sodium channels close until the cell has reached, or I should say that region of the axon, maybe to be more specific starting now, has reached +30. But they're really responding to that initial threshold. It's just kind of, we have a couple delay. So we'd measure in like milliseconds, I think like a 1 millisecond delay. Closing the sodium channel as that inactivation gate closes. And our potassium channels are also responding to that initial change in charge of hitting the threshold, but they're also slow, so they're opening around the same time as the sodium channels are closing. Because potassium channels are opening, bringing us negative, we don't get to that +60 that sodium wants to be at, that equilibrium potential. And also because the sodium channels are closed, so it's not getting in anymore. So during repolarization, so repolarization was that down part. So repolarization is here. During that repolarization, our sodium channels have closed, so they're not letting in more sodium. Our potassium channels are open, so potassium is escaping the cell. Potassium is positive, so the cell is becoming more negative. We call it repolarization because we're going back towards that -70. The re, right, means we're going back. but the potassium channels do stay open even a little longer. So like they stay open until we hit the -70, but you see now they're like closing, but some of them are still open. So we actually go a little bit below. So this region, we would call that after hyperpolarization. So after, meaning after this action potential, after this rapid depolarization event. Hyperpolarization being a term that we have seen before, basically meaning that we're getting very negative. We have some kind of inhibitory effect here on our memory potential. Once all the potassium channels have also closed, so now we're back to our initial state. We just have those leak channels open. The sodium potassium pump is going to be using ATP to re-stabilize our concentration gradient so that we go back to the concentration gradient that causes a chemical driving force that gives us our total electrochemical driving force. So basically it's resetting us back to how everything started at the beginning. Because since we've had all these things moving around, now we might not have as much sodium outside the cell as we did before because the bugs that came in, right? We've lost some of our potassium, so we need the pump to get those concentrations back right. So that's what's happening like between our -85 and our -70. So after hyperpolarization is just referring to that overshoot of -75. So it's when we drop down to -85. Doesn't get all the way down to -94 because they do start to close, right? Those potassium channels are closing. They're just not super fast at it. And our sodium potassium pump starts going. So we could number our phases. So phase 1 here would be the depolarization. Phase 2 is repolarization. And then phase 3 is the after hyperpolarization and the return to the resting potential. So I think the next couple of slides are just a flow chart, but we're at time. So any questions about this so far? Yep.
Is it always going to go past -70 and have to do the after hyperpolarization?
They don't always draw it that way, but yeah, that's kind of how it works. Next week we'll layer on how exactly this goes down the axon.
How did you say it like back up?
That's the action of the pump. The sodium potassium pump, yeah. Yeah, because remember the sodium potassium pump, right? We have 3 sodium out and 2 in, yeah. So like all these sodiums that we brought in during phase 1 are getting pumped out, and we're getting some of the potassium.